Okay, so let's consider that aircraft in the vertical loop, um, where let's say the pilot's effective, or we want to find the pilot's effective weight. In other words, the normal force in the pilot, says 78 kilogram pilot at the bottom of the loop. And so when we set up the free body diagram there, we have the normal force coming up, the negative force of gravity going down. And yeah, why don't you go ahead and pause the clip, and we'll compare this to what we have in space with that situation, and we'll see what the normal force is like. So go ahead and pause the clip, and you can try this, and then we'll go ahead and hit play to continue. Okay, so you set up your sum of the forces, positive normal force, negative force of gravity, and place your values in there. And then, yeah, if we wanted to find what the normal force is, that's pretty easy. If we're 80 kilogram person, we have our acceleration here. We have the force of gravity. What would the normal force feel? So this is what we would feel. If we were pulling 6 G's as compared to the just normal straight flight. Okay, so now what we're going to do is calculate the pilot's effective weight at the top of the circle. And so at the top of the circle, you're going to need a new free body diagram, a new sum of the forces, and we'll assume that the aircraft is still going 361.11 meters per second. And so yeah, why don't you go ahead and pause the clip and give this a try with the free body diagram, then the sum of the forces, figure out what the effective weight, what the normal force would be on him at the top, and that'll be good. So go ahead, do that, and then hit play to continue. All right, so at the top, we've got the force of gravity going down and the normal force going down. So hopefully, as you set up your sum of the forces, you have the positive normal force plus the positive force of gravity. Both are in the same direction. And because of that, the normal force doesn't have to be as much. We have the force of gravity acting with the normal force. They're both providing the centripetal force for the loop. And so we end up getting 3,821.97 newtons is the normal force. So not as much at the top. And that should make sense because both of those are pointing to the middle there. Now we're going to take a look at a situation where we have a ball that's spinning around in a circle, but the force of tension is up at an angle. So you can imagine this ball as it goes in the circle here, and it's being swung, and you have the force up at an angle. The tension is up like this. Let's say the length of the string is 48 centimeters and the angle is 60 degrees. We want to find what the angular speed is and the linear speed. Now, initially, you may think, you don't have enough information, right? You don't know the mass of the ball. All you know is just how long it is and the angle at which it's at, right? So you know that mass is probably going to have to cancel somewhere from here because you have the forces on it. Going. So go ahead, and the first thing I want you to do is write out or draw the free body diagram of the situation, and then so hit pause, and then you can hit play when you're ready to check that. Okay, so we've got our force of gravity straight down, and we have our force of tension. Now, if you think about it, right, this force of tension is up at an angle. We know that for this ball to go in a circle, it's got to have centripetal force, right? So it turns out, if we break this up, we have force of tension. This is centripetal force, and then we have the vertical force of tension here. And it's this centripetal force of tension that we're going to be concerned about, right? So that force of tension in the x is that centripetal force. So when we set up our rotational forces, we have our positive force of tension in the x equals ma. And that should make sense, right? This force of tension is providing that centripetal force. Now, if we put this in variable form, the force of tension in the x, we're going to put this in terms of what's going on with the mass, right? So if we think about it, this force of gravity, what's the force of gravity fighting, right? It's fighting that force of tension in the y, right? So if we think about that, the force of tension in the y here is equal to force of gravity. So in other words, force of tension in the y equals mg. Then from there, you should be able to use some trig to be able to put what is force of tension in the x then, if we know that force of tension in the y is mg and we know the angle. So go ahead and pause again and see if you can figure out how to put force of tension x in variable form. Okay, so when we set up the right triangle, we have the force of tension in the y set up as the adjacent side, and we have the force of tension in x, which would have been the opposite side. So when we set that up, we can set up the opposite over the adjacent, because we know the adjacent side is the force of tension in the y, and so we end up getting for force of tension in the x, mg times the tan theta. So now that we have that, we can work this out in variable form there. We can set this in here, and we know that the we were again trying to find the angular speed and the linear speed. Our unknown here, the radius, how will we know the radius? Well, we know that this length, the hypotenuse, is 45, right? So we can find the radius using trig. And that side is the opposite side, so sine is opposite over the hypotenuse, so sine of 60 times 45 centimeters, get 38.97 centimeters. So this is the radius as it goes in a circle. And yeah, from there we have everything that we need. So why don't you go ahead and pause the clip, calculate the linear speed and the angular speed, and then you can hit play when you're ready to check. Okay, so we've got that in there. Mass will cancel from both sides, and we'll solve for our linear speed, 2.57 meters per second. That's how fast it'll be going. And then we can get our angular speed, which would be 6.6 radians per second. And so, all that we started out with here is what angle it was at and the length of the string. And by leaving it in a variable form and thinking through the right triangles involved, we could figure out how fast it was going linearly, as well as how many radians per second. So as this goes around, right, the tangential speed, the tangent speed here, 2.57, we would have here.